Okay, looking at another example. So this time we're going to find the equation of the tangent line. We're given the function f of x equals 1 over x squared. They actually give us the point, negative 1, 1. If they hadn't given us the point, they might have just said x equals negative 1. We'd have to go in and figure out what that y value is at x equals negative 1. And let's even just show it. F of negative 1, we better get back a y value of 1. But if we plug it in negative 1, wherever we saw an x in this function, I can see right away 1 over negative 1 squared. Negative 1 quantity squared is positive 1, so this is 1. Okay. So you might just be given x. If so, you would have to go in and find the point. So we are finding the equation of the tangent line at negative 1, 1 of f of x. If we want to find the equation of the tangent line, well, for a line, we need two things. We need a point, which we have, and we need the slope. So we want to find the slope of f of x at x equals negative 1. So we need to find f prime of negative 1. So maybe I need to say this really quick, but if we're looking at the limit and we want to find it at, well, let's just do this. So we need to find f Okay, got disconnected. This is where I believe were left off. We were finding the equation of the tangent line again, 1 over x squared at the point -1, 1. In order to find the equation of a line, we needed two things. We need a point, which we're given, and we need the slope when x equals -1. And so we want to find, and we just learned this new notation, the derivative of x equals -1, which we can read as f prime of -1, or the derivative at x equals -1. And so we were first looking at the derivative of our function f of x. And once we find that, basically we can plug in any value of x where it's defined and see what that slope is at that value. And so now we're going to go into our function f of x. And we're going to plug in x plus h wherever we see an x. And so we have a limit here. Let's bring that down as h goes to 0. Well, if I'm plugging in x plus h, wherever I see an x in here, I would have 1 over that quantity, x plus h, and then it's squared. And then it says minus our original function, f of x. Well, that's just 1 over x squared. And then we're going to put this whole thing over h. So right now, if we did our direct substitution and we plugged in 0 wherever we see an h, you need to be careful. If you have more than one variable and you're looking at the limit, you look at which variable you're using. So this is as h goes to 0. And if we plug that in, we would notice that we get an indeterminate form of 0 over 0, and that didn't tell us anything, so we had to go back and manipulate it. So this is a complex fraction where you have fractions within fractions, and the one way that we can manipulate and work with this is by multiplying by a fancy 1, by clearing out our fractions within the fraction of our LCD of the fractions within this main fraction. And so there's only 2 fractions within this main fraction. And if I looked at my LCD, my least common denominator is equal to x squared times the quantity x plus h quantity squared. Doesn't matter the order. So we're going to multiply by this 1. And when we distribute in the numerator, all the fractions disappear. And that was the whole point of finding the LCD. And so when I distributed the first piece, notice that the x plus h quantity squares, h quantity squared cancels, and we're just left with x squared. When we distribute it to the second grouping in the numerator, our x squared terms cancel, and you're left with, we need to be careful, keep parentheses there, x plus h quantity squared. And this is all over h times x squared times the x plus h quantity squared. Okay, so we need to clean this up. Unfortunately, still, if we plug in 0 for h, things would, it would still give us 0 over 0. Let's not manipulate the denominator. Let's keep it in factored form. But let's go through. We want to expand this x plus h quantity squared, and then we're going to want to distribute that negative after we've done that. And so we have x squared minus, if you distribute out x plus h times x plus h, you would get x squared plus 2xh plus h squared all over h times x squared times x plus h quantity squared. So now distribute that negative to each term inside that parentheses in the numerator, and we're left with a limit as h goes to 0 of x squared. So distributing the negative, we get minus x squared minus 2xh minus h squared all over this h x squared all times x plus h quantity squared. You'll be able to see this x squared minus x squared, those cancel. And notice that in our numerator, we're left with each of the terms has a factor of h in it. So let's factor out that h so it cancels with the h in the denominator. And so if we pull out an h in the numerator, I'm left with a minus 2x. So parentheses minus 2x minus, and pulling out an h from the h squared, I'm left with a single h all over this h x squared all times x plus h quantity squared. And I need to bring down that limit as h goes to 0. So those h's now cancel. Now when we go back in and plug in 0 wherever we see an h, we should not get an indeterminate form anymore. So I would have negative 2x minus h all over x squared all times x plus h quantity squared. So again, we're going to do direct substitution. Wherever we see an h, we're replacing that with 0. Everything else is we're going to keep the same. And so we have negative 2x minus 0 all over x squared times x plus 0 quantity squared. So let's rewrite that a little bit. Notice once we plug in 0 for h, I dropped the limit as h goes to 0. And so here we have in the numerator negative 2x all over x squared times x squared. Rules of exponents, which you really need to get good at, and you'll be using that a lot once we get into not the formal definition of derivative to take derivatives. So same base and multiplication, we add our exponents. So in the numerator, I still have negative 2x all over x squared times x squared, which is x to the 2 plus 2 power, which is 4. Division, same base, we subtract. I'm going to keep the higher exponent in the denominator. So I'm going to take the exponent in the denominator and subtract off the 1 in the numerator. So 4 minus 1, I'm left with an x cubed. So this is f prime of x. This would give me the slope anywhere, if it exists, on f of x equals 1 over x squared. Well, we wanted to find the equation of the tangent line at x equals negative or positive 1. And so we wanted, oh, it was negative 1. So we want to look at what is f prime of negative 1. So looking at f prime of negative 1, so going into our derivative function and plugging in negative 1 wherever we see an x. So we get negative 2 all over negative 1 quantity cubed. So we get negative 2 all over negative 1 quantity cubed is negative 1. So we have 2 negatives, division is positive, so this is 2. So the slope is 2. We have a point on that line, tangent line, and on the graph, which was negative 1, 1. And so now we can find the equation of the tangent line by y equals mx plus b. So my y value is 1 equals my slope, which we found was 2 when x was negative 1 plus b. So we have 1 equals negative 2 plus b. So b now is 1 plus 2, which is 3. So we have y is equal to our slope, 2 times x plus b, which is 3. So they wanted us to graph this. Let me just pause for a second. Okay, so let me just kind of recap what just happened. So there was a chat, and I want to make sure, because sometimes you guys are finding little errors. I don't want to make sure before I go on. And so the chat was asking, can't we just use the derivative rule where we can just bring down the power down front, subtract one from our exponent? And so I know there's some of you guys that have had calculus before. And so unfortunately, we cannot use the general power rule, yet we have to use this formal definition of derivative. We need to use that limit of the difference quotient. Okay, so we're almost done with this problem, almost done with this lecture for today. We want to graph our function f of x, and we want to graph the equation of the tangent line when x equals -1. So let's do that. Okay, so 1 over x squared. There's a couple things you guys should know about this, and this is also probably a great way to review for what you guys are going to take a test on my math lab this weekend. Well, let's look at the end behaviors, or let's look at f of x equals 1 over x squared. We talked about vertical asymptotes. I can see here we have a vertical asymptote. Those were values which set our denominator equals 0, but not also our numerator. And notice that our denominator is 0 and x is 0. And so, and that x equals 0 does not make the numerator equal 0. So we have a vertical asymptote at x equals 0. And then recall, we can find horizontal asymptotes. One way to do it, let's just look at it that way. Let's look at the limit. Horizontal asymptotes are what is happening to our end behaviors as x goes to positive or negative infinity. And so recall, when you plug in positive infinity in for x squared, and that's in the denominator, and that's blowing up, we get 1 over infinity, because infinity squared is still something growing and just at a faster rate. This is equal to 0. Same idea, if I look at the limit as x is approaching negative infinity, and I plug it in for 1 over x squared, well, this is 1 over negative infinity squared, which is 1 over infinity, and this is still going to 0. So we have this horizontal asymptote on our x-axis, y equals 0. So horizontal asymptote, y equals 0. If we plug in values for x, we can also use other things that we've learned from algebra, that this is what type of function? It's symmetrical across the y-axis. So it's an even function. Okay, if I plug in values though, when x was -1, we got a y value of +1. I know my asymptote is looking like this. And that graph looks like that on one side, and it's symmetrical. And just recall even functions, just because I said it, I should write it. That's where if you plug in -x, wherever you see an x, you get back the same y value as your original function f of x. And that was symmetrical, and that doesn't, my picture doesn't look symmetrical, but you guys can picture that being symmetrical. And then we're gonna, that's our equation of f of x. Now we want to graph the tangent line. So mine might be a little off because of how I'm doing this. Let's say that was 1, this is 2, this is 3. So my units might not be great. Notice here, this is in, and this is one reason why I like to solve for my y-intercept and do it this way instead of the point slope formula. In this form, helps me graph the line pretty fast. I know what my y-intercept is. B is 3, so it's crossing the y-axis when x is 0. The y value is 3. And then my slope is 2. And we also knew this was a point here. So we could just join these two lines, or these 2 points to make a line. And so here's the graph of our tangent line and our graph of f of x. And if I blow it down so you can see the whole problem, I don't know if you I don't know if you can or not. So just let's do one more. This time, let's say that our function f of x is equal to the square root of x, and we want to find the equation of the tangent line. At x equals 4. Okay, so we need a point. And so find the point, we're going to plug in 4, wherever we see an x. So we're going to look at f of 4, which is equal to the square root of 4, which is equal to 2. Okay, so we know we have a point at 4, 2. We need the slope, and so we want to find f prime of 2. I can do this a couple different ways. I can do this just evaluating the slope when x is 2, and you might remember this. This was a limit of f of a plus h minus f of a all over h. This would give me f prime of a. Or I can find f prime of x. That would give me the derivative anywhere on the line or graph for any x value, and then I can plug in my value of x equals 2 there. So it doesn't matter. Because we don't have to find the derivative at more than one value of x, let's just do it this way. And this is what you guys were doing when we were looking at 3.1 instantaneous rate of change. So if I want to find f prime of 4, this is equal to f of 4 plus h minus f of 4 all over h. Oops, and I forgot to put in my limit here. And so doing that, if I plugged in 4 plus h wherever I saw an x and f of x, this is equal to, I got my limit, the square root underneath the radicals 4 plus h minus f of 4. But notice we already found what f of 4 was. F of 4 was 2, so minus 2 all over h. Unfortunately, we go back in, do direct substitution, plug in 0 wherever we see an h. You would see that we get the indeterminate form 0 over 0. And so that's where we had to manipulate it so we wouldn't get that form 0 over 0 anymore, and we would get back a number or something that was undefined. And so when we had radicals, and it was between two groupings, we multiplied by the conjugate. And so we're going to multiply by the conjugate, that is the change of the sign in between. So plus square root of 4 plus h over 2. Whatever we do to the numerator, we also have to do to the denominator. And there's our fancy one. We also talked about when we were multiplying by the conjugate, this was the difference of squares. And so using that fact, we can just square the first grouping minus the square of the second grouping. So f prime of 4 is equal to the limit as h goes to 0. So squaring this first grouping, the square root of 4 plus h quantity squared is just 4 plus h. Minus, and then the square of the second grouping, which is 2. So minus 2 squared, which is 4, all over this h times the denominator. So parentheses square root of 4 plus h, and then outside of that is a plus 2 and your parentheses. So now as this simplifies down, the 4's cancel. And once the 4's cancel, we have an h, single h in the numerator all over the denominator. That one of the factors is h, so that's going to cancel. So if you want me to write it, this is limit h goes to 0 of h all over h times that parentheses square root of 4 plus h plus 2. H's cancel. So we get f prime of 4 equals the limit as h goes to 0 of 1 all over the square root of 4 plus h plus 2. Direct substitution now. We find f prime of 4 is equal to the numerator of 1 all over the square root of 4, which is 2, plus 2, or 1/4. So we found that our slope was 4, 1/4. We found our point was 4, 2. And so now we can find the equation of the line really quick. Y equals mx plus b. Y is 2 equals my slope 1/4 times x, which is 4 plus b. So I get 2 is equal to 1 plus b. Subtract 1 on both sides, we get b is 1. So equation of the tangent line is y equals our slope 1/4 times x plus 1. And that's what they were asking us to find, was the equation of the tangent line at x equals negative, or x equals 4 in our case.